For which of the following quadratic surfaces is it possible to intersect the xy plane as a pair of intersecting straight lines, and for any plane of the form z equals a constant intersects as a hyperbola? And we have some options: ellipsoid, hyperboloid of one sheet, hyperboloid of two sheets, hyperbolic paraboloid, elliptic paraboloid. A, B, C, D, or E. What's the answer? D. Now, let's just make an observation. It's probably not A or E, right? Just the names. Because you're looking for hyperbolas, you should think, what has hyperbola cross sections? Ellipsoids look like circles or ellipses. And elliptic paraboloids look like circles or parabolas. So even if you're just guessing, please don't just guess A or E. Put some thought into your guesses. And the correct answer is indeed D. The hyperbolic paraboloid. Now, it's not so clear when you think about the hyperbolic paraboloid why you would get a pair of intersecting straight lines if you hit z equals 0. Well, suppose we write our hyperbolic paraboloid in one way. This is one way to write it, as z equals negative x squared over a squared plus y squared over b squared. Well, if you plug in z equals 0, that gives you a relationship, and in particular x squared over a squared equals y squared over b squared, which says x over a is plus or minus y over b. Which means you have two intersecting lines that go through the origin. So indeed, it is D. I will say that this question is a little bit very carefully phrased in that it says which of the following quadratic surfaces, but not for which quadratic surfaces. Because if you change it to say which quadratic surfaces, it turns out D is not the only answer. Do you know any other quadratic surface where you might intersect it in some way and it looks like a pair of lines that cross, but then if you shift where you intersect, you get hyperbolas? Spoiler alert, it's not on that list. The answer is a cone. And so, in particular, we can draw our cone tilted sideways so that it shrinks down to the origin, then it crosses over and it gets big on the other side. Now, as you slice at z equals 0, you're going to get these lines that cross through the origin. But what happens if you move it up, where you're capturing a piece of the cone? And it turns out there's a nice fact. I don't know if I mentioned this, but hyperbolas are what are known as a conic section. A conic section means you get it from slicing a cone. And so if you move up your z a little bit, then what happens is you're just going to get a pair of lines, and that's a hyperbola. So, all right, good. Okay, well, fun problems, right? On to problem solving. So, we're talking about how to solve problems. Let's recap. Step 1 is understand. You can't solve a problem if you don't know what it's asking. Step 2, make a plan. So the third step, carry out your plan. Because if you're going to solve a problem, at some point you should solve it. So this is the actual solving part. And, okay, you might say, well, there's not a lot to say here, is there? Well, there's not too much to say. This is fairly short, but there are a couple of things. One thing is, can you check each step? You should get into the habit of saying, look, I want to learn to catch my errors. I don't want the grader to catch my errors because they're going to take points away. I'll catch my own errors and fix them. And then the grader will give me all the points. Got to get them all. Got to get them all. So, make sure. Think about ways to check your work. Pause. Think about what's going on. And can you follow your solution? Is it organized? it turns out it's a lot easier to check your work if you understand what you did. And we sometimes get these solutions back, and we love our students, but we have the darndest time, excuse my language, I'm a little salty today, the darndest time trying to figure out what in the world is going on. Everything just seems highly all over the place. And the more unorganized it is, the harder it is to follow your work. And it's true. It's harder for you to follow. It's harder for the grader to follow. So learn to be organized. Be methodical. And also, be ready to adjust. Sometimes you think a problem is going to go one way, but we get a step or two and you say, oh, well, isn't that interesting? That's not what I was expecting. So be adaptable. All right. So quick recap from last time when we did our sprint. We talked about quadric surfaces. And the main thing we tend to ask in relationship to quadric surfaces are matching type problems. We'll look at an example in a minute here. But they do come up with some very nice examples for us to work with. We'll work with many from time to time, but the two most important that we will mention highly as we get into the second portion of the class are the elliptic paraboloids and the hyperbolic paraboloids, which are going to be your bowls and saddles. So those aren't just interesting examples, those will be sort of important examples. So you want to make sure that you have those and that you understand them going forward. One thing that I didn't point out, but I think it's kind of interesting to note, is that some of these are much closer than you might think. So for instance, the cone, the hyperboloids, are actually all very close one to another. So, which is to say that you can get from one to the other by a small perturbation. So, in other words, let me point to say this plus one. If you started playing with this parameter and said, well, suppose I drive this value down to 0, what would you get? You'd get a cone. And then he said, well, suppose not only do I drive it down to 0, then I start moving it in the other direction. And what do you get? Well, it's a hyperboloid of two sheets. So in a very real sense, you can say, well, look, you can think of these as sort of as families that build, and you can deform. So you have the cone, which can fit inside a hyperboloid of two sheets, which then inside of the cone, you can put in hyperboloid of one sheet is on the outside and a hyperboloid of two sheets inside the cone. And we'll talk about this a bit more in about a week, I think. So something to look forward to. All right. So as I mentioned, we like matching problems. So here's a problem from an exam, old exam. We have 5 given formulas for surfaces. So here are our formulas for surfaces, and they all are quadric surfaces. Now, there are some things that might be slightly different. You might interchange the role of x, y, and z, which more or less just means you're basically turning it 90 degrees in some direction. So the goal is, can you match the equation to the picture? And you might say, wait a second, I see 5 slots here. I see 8 pictures there. That's right. We put in more pictures than equations, so you have to figure out which ones are important and which ones are not. Let's start with the first one. Y squared plus z squared equals x. Do we have an answer for that one? C. Yes. That is correct. What's some clues here? What kind of shape should you be looking for? It's a bowl type thing, but what's sort of different from the bowls we've talked about? Because normally we said, oh, z equals x squared plus y squared. That would be a bowl opening up, because this is a bowl over here. So why is it not f?
Dimensions are switched.
Well, yeah, so we changed our directions, right? So x is in this direction. So that's why you have the x equals y squared plus z squared is this bowl, which has been turned on its side, spilling out its contents onto the floor. All right, second one. X squared minus y squared equals 4. Gee, what's the clue here? There's no z. If there's no z, it means it should look the same for any value of z. So it should be basically a photocopy up and down. Which one of these photocopies up and down? G, it's the only one. All right, z squared minus y squared plus x squared equals 1. What's that? H, that is correct. What kind of surface are we dealing with? It's a hyperboloid of one sheet, and there's only one hyperboloid of one sheet drawn. So that's H. And you can see there's sort of the central axis is in the y direction. All right, x squared plus y squared over 9 plus z squared over 25 equals 1. Which one is that? A. Okay, good. Easy to spot. What kind of surface should this be? Ellipsoid. And one thing about ellipsoid, it's the only one that's sort of contained. All the other surfaces keep going forever, but the ellipsoid doesn't. And so all these other surfaces kept going, but A stayed within its little tiny ellipsoid type shape. One left. Y squared minus x squared minus z squared equals 1. Which one is that? It is D. Correct. It's a hyperboloid of two sheets, but again, you've swapped your directions. And all right. So we didn't use some of these. We didn't use F. We just had to distinguish between the two bowls. What kind of surface is B? Cone. Good. What is E? Saddle. All right. Good. Now we're ready. We're ready. Anything they could ask us about quadric surfaces, we're good to go. Which means let's start thinking more about calculus. It's been a while, but at some point we had to talk calculus. See, look, it says the word calculus there. So calculus is in sight. All right, so what's the goal for today? Well, we want to talk about parametric curves. So you can think of it as there's a particle that's traveling through space, and it's taking a very strange journey, but off it goes. You might say, well, how can you describe what's happening to this particle? Well, what you can do is say, where is the particle at any given time? So you say, all right, well, let's mark, here's our particle, and we can give it its location, x of t, y of t, z of t. So this is what we mean by a parametric curve. The parametric part means there's a parameter. The parameter is time. Where are you at any given time? I'll give you a location. Then as time varies, your location varies. You are moving. Now, this is wonderful and intuitive, but a little bit difficult to work with. Hard to do the calculus stuff. So we have a great, but what if? And we say, let's change these parentheses on the end. Right now, it's a point. And I'm going to think of associating every point with a vector. So I'm going to think of this as a vector x of t, y of t, z of t. So in particular, I think of it as I nail one end of my vector to the origin, and then I have the tip of the vector, the arrow part, following along on the curve. And that helps me see what's going on. All right. And that gives us a vector valued function. So for every single time t, I get a vector. And I interpret that vector saying it's really pointing to my location. It's saying where I'm at. So it more or less feels like you're doing the same thing. Just do you do it as a point or do you do it as a vector? And so it doesn't feel like you've gained much, but you kind of have. Because there's things you can do with vectors that you can't do with points. And when I say you can't do, in other words, there are things that geometrically make sense with vectors that geometrically don't make sense with points. And namely, you can add vectors together and you can scale vectors. Now that doesn't seem like a big deal, but it turns out that calculus needs 3 ingredients. You need to be able to add, you need to be able to scale, and you need to have the notion of limits. If you can do those 3 things, you can calculus on it. So, because we can add and scale vector value functions, and we can talk about limits. So, what does it mean for limits? You have to get notions of closeness. Because limits are saying, well, what should happen? And you figure out what should happen by saying, well, what's happening nearby? What's happening if you're close? And, well, 2 vectors are close only if their individual entries, their individual components are close. And so the punchline is you work entry by entry. And so no big surprises. You work entry-wise. So this is sort of the big idea. And it's not a very surprising idea. And more or less it says, you know, these are all going to feel like Calc 1 problems. But now, instead of doing 1 small Calc 1 problem, you're going to get to do 3 small Calc 1 problems. 1 for each entry. So that's the good news. Things to look forward to, right? Okay. All right, so we can talk about locations in space. So the next thing is, well, can we talk about tangent lines? Okay. We have to decide what that means. So we have some curve floating in space. And we say, all right, well, suppose I want to talk about this point right here. And when we talk about tangent lines, there's this intuition built in that says, what do we mean by a tangent line? Well, it means that if you were to take a very powerful zooming in device and zoomed in on that portion, then what would happen is that you'd see something which is very straight. And if you zoomed in far enough, it would be so straight that it would be imperceptible from a straight line. And so you say, okay, so the goal is we say zoom in, and eventually we look like a line. So there's our tangent line. That's the intuition that we have. So again, over here, there's our tangent line. So we have to start thinking about how do we make a line? What information do you need? And there's a list. It's a very short list. Every line that you ever make, you're going to have to do 2 things. You're going to have to find a point, and you're going to have to find a direction. And so we're going to mark this line, and this is our notation. And I don't know why they chose the letter R, but just they did. So R of t, we're in 3 dimensions, x of t, y of t, z of t. So we have our parametric curve, and we say, all right, well, how do we get our point? Well, the point's not hard. The point's, it's a freebie. So it follows from automatically. You just say, you pick a time, and then you plug it in, and that's pointing to your point. So it's just the value of the parametric curve at the time you're interested in for the tangent line. Okay, well, that's not so bad. Well, how do you get the direction? All right, now that one's a little bit more interesting. So, we have to think a little bit about how we move along the curve. So, let's suppose here is the time at A. Put on your old Calc 1 hats. You may have to dust them off a little bit. Say, how did we find our slopes? What was our basic idea? I mean, like limit definition. Do you remember that? Right? Like, oh, yeah. I know how you feel. It's like, oh, I miss those days too. Ah, the good old days. We were so young and innocent back then. But the idea was you say, just move a little bit. So you say, okay, let's move a little bit on the curve. So here I've moved a little bit further down. And if you look at this direction vector from r of a plus h to r of a, you'll notice it's very, very close to the direction vector of the tangent line. Now, it's not exactly the direction vector. It's going to be a little bit off, but not bad. So we say, okay, so the direction vector is approximately, this is our intuition, r of a plus h subtract r of a. And now, because this is getting small, let's go ahead and divide by h. Because r of a plus h minus r of a is very, very tiny entry. So if you divide by h, that helps avoid things getting too small. Because we don't want our direction to be 0. That would leave us directionless. We don't want that. And now we look at this and say, how do we get a better estimate for our direction vector? What should you do? You should do a limit. So our direction vector, it's a good approximation if h is small. The best approximation is if you say, well, what happens as h goes to 0? R of a plus h minus r of a over h. Well, that's your derivative. And if you remember, we said, hey, when we think about taking derivatives, we do them one entry at a time. And so when you look at your x entry, it's like you're taking the derivative of the x entry. When you take the y entry, it's like you're taking the derivative of the y entry, and so forth and so on. We call this r prime at a. All right, so the value of the function, that gives you location. The derivative gives you motion. We're going to talk about this a little bit more in the next lecture, but the key thing here is that the derivative, it helps give us the direction of the tangent line. Okay, so we'll make a couple of comments here. So for r prime of a, you take the derivative, and no surprises here, entry-wise, one entry at a time. Okay, well, let's make up an example. We can do that. We're pretty good at making up examples. So, we'll do it together. Find the tangent line to r of t equals. So, what do you want in your first slot? Pick a function. Function of t. T squared. All right, anything else?
Plus 2.
Plus 2. All right, now we get a second slot.
T minus 3.
T minus 3. Oh, you're hoping for us to be nice on your exams. Obviously, you haven't taken enough exams yet. No. We're nice people. We're nice people. Third slot.
Natural log of 3x squared.
Okay. Now, I like your spirit. Very good attitude. I think you said natural log of 3x squared?
3t.
3t squared. Good. I was going to say, hold on. Now, just because I want to make sure we're defined for all t, I'll throw in a plus 1 here. That way we'll never have to worry about, like, oh, am I taking natural log of 0? Or, oh, am I taking natural log of negative? It's like, nope, we're good. Everybody's happy. Now, what else do we need to know about finding the tangent line? You have the curve. What else do you need to do? What else do you need to know? You need to know at what point. And points are given either explicitly as points or as time. Hopefully they give you as time, especially in a case like this. But let's suppose they gave it to us as a point. And let's see if we could crack their code. At the point 3, negative 2, log of 4. If they gave it to us like this, which is fine, what would we need to do? Solve for t. So how do you figure out t? Well, you say, look, I need t squared plus 2 to equal 3. I need t minus 3 to be negative 2. And I need log of 3t squared plus 1 to be log of 4. There will be only one t value that makes all those true simultaneously. At least hopefully there's only one. Do we see a t value that works? 1. Oh, that was convenient. So we can translate, if they give us a point, we can translate that to a time. if they only gave us the time, how would you get the point? Plug it in. So point is pretty quick. What do we need to do next? Take the derivative. All right, so here we go. Taking the derivative. We're going to take it one piece at a time. Derivative of t squared plus 2. 2t. Derivative of t minus 3. 1. Derivative of natural log of 3t squared plus 1. 6t over 3. All right, good. Yes, all right. Nice. Okay, 6t over 3t squared plus 1. And those who might be wondering, like, whoa, that was pretty quick. What happened? So whenever you're taking the derivative of natural log, 1 over the inside. So that's why you get a 3t squared plus 1 downstairs. Then take the derivative of the inside and you throw that upstairs. The derivative of 3t squared plus 1 is 6t. Now, is this our direction vector, and why not? No, it's not our direction vector. Why not? Well, it's got t in it. What do we need to do with this? We need to plug in and evaluate. So it's not the direction vector until you've done your evaluation. Okay, so we plug in 1. R prime of 1 is 2. 1, that was easy. 6 over 4. 6 over 4 is the same as 3 over 2. Okay, are we done now?
No, you need to do that's not a line.
It's not a line, right? Remember, you always have to make sure you give the answer in the way that was asked for you to give it. It said, find the tangent line. What we found are the pieces that you need to make the line, but just because you have the pieces doesn't mean you have the line. You have to go that last step to write down the line. Now, we can write it in vector form or in parametric form because it didn't tell us one or the other. Which one do you want? Well, you can use both, but that just extra time to write. I don't know if I have enough space to write both this time. Let's do vector. Okay, if I'm doing it in vector, then what you do, you write your point as a vector. So 3, negative 2, log 4, plus, and then you have an entry here. We almost always use t. This can be a little bit misleading because if I write t here, it's not really the same t as there. Can I use a different symbol? How about tau? For all those Greek fans out there, this is a small tau. Not to be confused with the capital tau. 2, 1, 3/2. And there's the line in vector form. If you put t, you'd be okay. It's just you have to be very careful when you have questions involving tangent lines to make sure you understand this t is not that t. So that's why sometimes it's better not to even go down that line and say, look, I'm not even going to think about it. Not even going to harbor the idea that they could be the same. All right. Well, any questions about tangent lines? Okay. A few comments. Derivatives work entry-wise. And the nice thing is, that means that you're really taking the derivative of each single entry. And as a consequence, you say, look, anything that's true for each entry, you can then extrapolate, and it should be true for all the entries. So here, when you see a capital F of t and capital G of t, so F of t, capital F of t, capital G of t, these are vector valued functions. So in other words, you have your input as time and your output as a vector. And little f of t and little g of t, these are what we call scalar valued functions. And that says your output is a number. But these work intuitively. So the first thing says it works well with addition and arithmetic. So if I have a bunch of things being added, I can take the derivative of each part. If I have a constant, I can pull it through the derivative. Another way of saying that is that derivatives are linear. So this is linear. You can also talk about the chain rule, but you have to be a little bit careful here how you put one function inside of another, because it doesn't always make sense. So here I have a scalar valued function inside of a vector valued function. And the claim is if you take the derivative of the outside, leave the inside as is, times by the derivative of the inside. That sounds familiar. What is that? It's the chain rule. And this is actually just says, hey, the chain rule still works. Okay. Now, the last thing on here, there's 3 variations of the product rule. So the 3 variations, because we have 3 ways we can multiply. You can take a number times a vector. That's this first piece. That's scalar product. And you say, well, do the obvious thing. You can take a vector dot a vector. That's dot product. And you say, okay, well, do the obvious thing. We take derivatives. And when I say the obvious thing, derivative of the first with the second plus the first, derivative of the second. I often think of it as everybody gets a turn, right? It's like, well, I have 2 functions involved. They all want to have their turn to be a derivative. It's like, okay, everybody gets their turn one time. And so derivative of the first, leave the other one alone. Leave the first one alone, derivative of the second. So that's how you get that expression. And very happily, it's even true for cross products. So these are all 3 variations of the product rule. Now, I won't go through and prove all of them, but how about we do the chain rule? That one doesn't take too long to prove, just to convince ourselves of how these arguments work. So let's let f of t be our vector value function x of t, y of t, z of t. So f of g of t, that would be, I'm now, everywhere where I used to have a t, what goes in place? G of t. So this will become x of g of t, y of g of t, that's a y there, and z of g of t. So now take the derivative. And the moral is we take the derivative entry by entry. So we can now go back and say, hey, we have our old chain rule now. So we apply the old chain rule. We get x prime g of t times g prime of t. And then we go to our second entry and say, oh, we still have our old chain rule. Y prime g of t, g prime of t. And same for the third entry, z prime g of t times g prime of t. So all these rules fall from the old rules, just applied in the appropriate places. Now, it's very compressed here on the screen, but what do all of these 3 terms have in common? They all have g prime of t in common. It's a common factor. If it's common, you can pull it out. So we pull it out, and we'll put it on the end. There's no reason we have to put it at the beginning. So x prime g of t, y prime g of t, z prime g of t, times g prime of t. But this part, that would be what results from taking f prime and just plugging in g of t. So you have f prime g of t times g prime of t. So all these rules really do follow from the rules that we did before. Okay. Any questions? All right. Let's do another problem. So here's a curve. R of t, e to the 3t plus 2, cosine t plus 4t, and 2 secant t minus 5 arctangent t. So we have those 3 slots. And this is a happy day. I don't know if we've had a chance to say the word arctangent in our class, but it warms your heart when you get to see it. All right. Find the plane which perpendicularly intersects the curve r of t at time t equals 0. So you're not after a line, you're after a plane. So find the plane which perpendicularly intersects the curve r of t at time t equals 0. If you see this problem, my eye is drawn to a word here. Well, because I purposely wrote in a different color. So plane. So thinking about this, what should you be trying to do to find a plane? A normal vector and a point, right? So you see plane, you start thinking point and normal vector. So what's the point? Not like philosophical question, like what's the actual point in space? Yeah, you know, plug in r of 0. What's the normal vector going to be?
The line that's perpendicular to the tangent line?
Well, so we're going to use the direction of the line, in particular the direction vector of the curve will become our normal vector. So did we get an answer? Everyone said, I found it. This is what I got. So take the derivative, and again, it's like 3 small Calc 1 problems. Oh, I know, it's been a while since you saw the derivative of arctangent. You can expect to see it again. So, I'm not saying it'll be on the exam. I'm not saying that. I'm just saying I like examples that are interesting. And so take your r, plug in 0, you get the point 312. Plug in 0 to the derivative, and that's the direction vector of the line. If I want to be perpendicular to the line, I should be perpendicular to the direction vector. That's the normal of the plane. That gives me my coefficients. Use the point to figure out what goes over there, and thus we get our answer. Okay. All right. Well, good. We do need to do one quick fact, which will be important next week. It won't seem important right now, but it'll be important next week. Suppose you have a curve that has constant magnitude. Now, intuitively, if I'm on a curve that has constant magnitude, what does that say about the curve? I mean, what's the magnitude of r of t measuring?
How long is it?
It measures length. So someone said length. Length to where? The origin. So if I have constant length to the origin, where am I living? On a sphere. Yeah. So constant magnitude says, hey, it's like you live on a sphere. So there's some big round object. And so you have to imagine that perhaps you lived on a big round object. Just use your imagination as best you can. Okay, I live on a big round object. And the point is you have this curve that's just traveling along the surface. And now the claim is if you look at r of t and r prime of t, at any given time t, they're perpendicular. All right, well, how can we prove this? Let's see if there's some hints. We're trying to tell two things are perpendicular. What's a way to tell if two things are perpendicular? Dot product. So say, oh, there's a big hint here. So r of t dot r prime of t, that should equal 0. Now, is there any relationship between dot product and magnitude? Good, yes. What's the relationship? What happens if you take r of t dot r of t? Well, you get the magnitude squared. That's where we start down our road of saying r of t has meaning, because we get this fact. So, let's take the derivative of the magnitude of r of t squared. If it has constant magnitude, what's the derivative of this going to be? 0. So that's the derivative of r of t dot r of t, because you can compute the magnitude squared by a dot product. What can we do to take this derivative? Product rule. Derivative of the first, dot the second plus the first dot the derivative of the second. But it doesn't matter which order you take the dot product. So this is 2 r of t dot r prime of t. What's our conclusion? It's equals 0, so they are indeed perpendicular. All right. Normally at this time, we would throw up a multiple choice problem, and then we would say, oh, think about it for 30 seconds. Okay, there's our 30 seconds. You can see, it's very similar to the one we just did. So